This is Dr. GVR Seshagiri Rao, Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So today we will discuss about keys and couplings. So how to solve the keys and couplings problems I will explain. So first we will see one problem on a rectangular key. So various keys are there. Already we have studied in a previous session. So rectangular keys and square keys. So saddle keys and sun keys. Give a head key. So all these keys you have to design as per design standards. The keys are useful in design of shafts problems also and couplings also. So the function of the key and what are the materials of the key, how to calculate how to write the torque transmitted equations already we have studied. So now, so in this session, so I will explain, so how to solve the problem. So when I given a particular key, rectangular key design or a square key as per dimensions. In this problem, so he has asked the first problem is design the rectangular key. The type of key is here rectangular key. So for a shaft of 50 diameter. So the diameter of the shaft is very important in designing of keys. So the each and every dimension depends upon the shaft diameter only, the in keys and couplings also. The shearing and crushing stresses for the key material, shear stress and crushing stress for the key material are given 42 megapascal and 70 megapascal respectively. So these two stresses have to check after designing, have to checking for shear strength and checking for crushing strength. So the calculated shear stress or crushing stress should be less than these given stresses. So these are the permissible stresses. So, always the component should withstand. So given permissible stresses. So how to check these permissible shear stress withstand or not? With the comparing with the calculated shear stress or crushing stress, that always the shear stress value or crushing stress value should be less than the given permissible stress. So then only the above design is safe. So I will explain in the later slides. The first given data. So write down the given data. T is equal to 50 diameter. So the diameter of the shaft is 50 The shear strength for the key material given 42 megapascal. Convert into Newton per square. So already you know 1 megapascal is equal to 1 Newton per square. Clear? So convert into Newton per square. The sigma C is equal to 70 megapascal, 70 Newton per square. So already you know this 1 megapascal is 1 Newton per square. So how to convert units from Pascal to Newton square? So once again I will explain. So 1 megapascal is equal to 1 into 10 to the power of 6 in Newton per meter square. So convert into Newton per square. So divided with 10 to the power of 6 in Newton per square. So here 10 to the power of 6, 10 to the power of 6 get cancelled. So now finally you will get 1 Newton per square. So that you can write directly 1 megapascal is equal to 1 Newton per square. So that here written 70 megapascal is equal to 70 Newton per square. The length of the key is obtained by considering the key in shearing and crushing. So first assume the length of the key, take L. Considering shearing of the key, already we know the shear strength are transmitted by the key. So how to calculate by using torque transmitted equation. So first write down the torque transmitted of the key. So T is equal to L into W into tau into D by 2. So L into W, this area, and then tau into d by 2, the torque transmitted equation. So that here L we don't know, need to calculate. So W not given, but 16 here substituted. So how to calculate for rectangular key? The rectangular key dimensions are, for rectangular key, suppose for rectangular key, this is width and thickness or h. B. So rectangular key. So like this length and the cross section here B. The dimension B and h or t. So here the thickness is, two dimensions are there here, width and thickness or h. So width is equal to d by 4 and thickness or height is equal to d by 6. So here d is shaft diameter. For square key, width and h here both are same. W is equal to t is equal to d by 6. So like this, first we have to calculate W and width. So that here 50 divided by 4 we have taken. So here D is 50. So D by 6. So 50 by 6. 50 by 6 is equal to here. So 8.33. So that here you can take, you may assume the standard thickness is 10. Similarly, width is equal to the standard thickness. Width is equal to 16. So now substitute these values in this equation. Already shear stress given 42 and diameter also you know. So you will get 16,800 L. In terms of L, you will get. So you need to calculate L value. And torsional shear strength or torque transmitted of the shaft is T is equal to 5 by 16 into d cube. 16 into tau into d cube. Already you know this torsion equation. Here 5 by 16, given shear stress is 42 and diameter is 50. So that the available obtained torque is 1.03 to 10 to the power of 6 Newton mm. So now this torque value equate with this 16,800 L Newton mm. So now calculate L. So here torque is equal to 1.03 10 to the power of 6 Newton mm is equal to this 16,800 L. So that L is equal to 1.03 10 to the power of 6 divided by 16,800. So now finally you will get 61.31 mm. So now considering the crushing of the key. So in previous case only you have considered shear strength. But in your problem given shear strength and crushing strength. So both we have to take. So we know that the shear strength are transmitted of the key when the crushing stress of the key is considering. So again write down the equation. The equation is T is equal to L into T by 2 into sigma C into D by 2. Here sigma C is the crushing strength and L into T by 2, the crushing area. So here in previous case, the shear area is L into W, the shear area. But in this crushing, L multiply with thickness is T by 2 and T by 2. So in this area, you need to calculate crushing area. So now substitute L into, again need to calculate L value. So don't substitute above calculated L in this equation. So T by 2, T thickness of the key, and sigma C given in our problem, crushing strength 70, and then 50 by 2. So finally, obtained value is 8750 L Newton mm. So based on crushing strength of the key, obtained 8750 L. So again this value equate to torque transmitted. Sorry, this one is the torque transmitted. Convert into, equate into this equation 5 by 60 torsional crushing strength. So again find out L. So here T is equal to 5 by 16 12 into D cube. So 1.06 into 10 to the power 6 Newton mm. So that 1.03 10 to the power 6 is equal to say 8750 times of L. So that L is equal to 1.03 10 to the power of 6 divided by 8750. So calculate. So obtained value is 117.7 mm. So now we have two values. One is obtained from shear strength, another one is obtained from crushing strength. So that take the larger value of the above two calculated values. So in the second case 117.7 and the first case L is equal to 61.31. So larger one is this one. So that you can fix this length as a final length of the key. So the 117.7, the standard length of the key is 120 mm. So this is your final length of the key. Like this, how to calculate. So in previous case, we have learned a rectangular key problem. Suppose in place of rectangular key, square key is available. So then the square key dimensions need to substitute. The square key width and thickness or height of the key are same. So only that is the difference between the rectangular key and square key. The remaining calculations are same. Now I'll explain in this session. So take one coupling problem. So various types of couplings are there. So mainly classified into rigid coupling and flexible couplings. Rigid couplings are, so already you know the couplings in the coupling section already I have explained here. One is rigid type, rigid and flexible. Again, rigid couplings are classified into muff coupling and planes coupling. Flexible coupling are bushed pin type coupling, bushed pin type coupling, universal coupling. So these are all are classified under flexible coupling. So now in design part, how to calculate all the design parameters of a given coupling. So given a problem is here muff coupling. So the muff coupling comes under rigid type coupling. So the difference between the rigid and flexible coupling already we have explained in earlier sessions. It does not allow some angular misalignments, but whereas in flexible coupling it allows angular misalignments. They will take. So that's why the rigid and flexible couplings are separately how to design. So design and make a neat dimension sketch of a muff coupling. So first you have to design and then need to draw a neat dimensional sketch of a muff coupling as per obtained design parameters. So this is used to connect two steel shafts transmitting 40 kilowatts at 350 rpm. So the given power is 40 kilowatts and N is equal to 350 rpm. So the material for the shafts and key is plain carbon steel. So the material of the shaft and key is given plain carbon steel. According to given material, need to assume so if any data is required, for which allowable shear and crushing stress may be taken as 40 megapascal and 80 megapascal. So these values also given 40 megapascal and 80 megapascal shear and crushing stresses respectively. The material for the muff is cast iron. So here the muff is different material, cast iron, and the key and shafts are plain carbon steel, which the allowable shear stress may be assumed as 15 megapascal. For muff case, the allowable shear stress is 15 megapascal. For the key and shafts are 40 megapascal and 80 megapascal. So now, we will see how to solve this type of coupling problems. First of all, given data. For any design problem, first you need to write the given data. Power available, the given power is 40 kilowatts. So convert into watts. So 40 into 10 cube watt. And then 350 rpm. And shear stress 40 megapascal, convert into Newton per mm square. Similarly, 80 megapascal crushing stress, convert into Newton per mm square. Crushing strength, shear strength for the muff material is 15 Newton per mm square for cast iron material. For plain carbon steel, 80 megapascal, and for cast iron, the material, the shear strength is assumed as 15 megapascal. For any coupling problem, so the design of shaft is important. So design of shaft means diameter of the shaft is very, very important. First need to determine the diameter of the shaft. The remaining all values are depends upon this diameter of shaft. So here shown the diagram of the muff coupling. Muff coupling figure. So here muff coupling, two shafts are connected with this alpha for muff and key. Shaft 1 here and 2. These two are connected with the help of this muff. Muff dimensions are L, length of the muff, and the diameter of the muff, capital D. Small d is the shaft diameter, and key dimensions already you know. So now in calculation part, first design for shaft. Let assume d, small d is the diameter of the shaft. So you know that torque transmitted by the shaft key and muff, T is equal to, actually the power equation is 2 pi and T by 60. So T is equal to 60 P by 2 pi N. So may be written like this. The P is given power and speed. Now in this equation substitute the given values. Power value already you know given in our problem, 40 kilowatts, convert into watts, 40 into 10 cube into 60 by 2 pi into N. N is the RPM, the shaft RPM. So now calculate now 1100 Newton meter uptime. So this value convert into Newton mm. After that, apply torque transmitted equation. So torque transmitted equation is T is equal to pi by 16 tau into dq. So obtained this equation from a torsion equation. So that here torque already we calculated 1100 Newton meter. Substitute those value in this equation. The shear stress for the shaft material given 40, and diameter we don't know, need to calculate diameter of the shaft. So apply this equation. So after calculation, so obtained value is, so substitute 1100 Newton mm by this 7.86 d cube. So d cube is equal to, obtained value is 140, the d cube is 140 into 10 cube mm. So d is equal to, obtained value is 52. So you can say 55 as per the standard dimensions of the shaft. So next one, the second step is design for sleeve. The sleeve nothing but muff. It's already shown in this diagram. So muff or sleeve. The sleeve having inner diameter and then outer diameter. The outer diameter is D, inner diameter is nothing but shaft diameter. The shaft diameter is shaft dia and outer dia. Clear? So the here shaft diameter is inner diameter of the muff or sleeve. The outer diameter you need to calculate. So that take the standard empirical relation, the outer diameter of the muff is 2d plus 13. D is equal to 2 times of the shaft diameter plus 13 mm. So now substitute the standard diameter of the shaft taken as 55 in this equation. 2 into 55 plus 13. So 123 obtain. So take the standard diameter 125. So length of the muff taken as L is equal to 3.5 times of D. L for the muff, for the given muff 3.5 D. Suppose in case of keys, L is equal to 1.5 times of D for keys. These are the standard diameter, standard empirical relations between length of the muff and diameter of the shaft, and length of the key and the diameter of the shaft. Now here the obtained is 195 mm. So now check for the induced shear stress in the muff with the given values. So let assume the induced shear stress is tau c in the muff for the cast iron material. So in our problem for the cast iron material, the given shear stress value is 15 megapascal. So if this value is safe or not, have to check. So how do you check here? By using this equation. So here consider the muff or sleeve as a hollow shaft. Consider to be a hollow shaft. For a hollow shaft, the diameter, the torque transmitted equation is for solid shaft already you know. Solid shaft 5 by 16 into tau into dq. This is for a solid. For a hollow shaft, T is equal to 5 by 16 shear stress into d to the power of 4 minus d4, d small d to the power of 4 by capital D. Yeah. You may write in terms of ratios also in inner diameter to outer diameter. For simplification, you may use K value also. K is equal to di by d naught, inner diameter to outer diameter. So here outer diameter is muff outer diameter, d small d is the shaft diameter. So all values already we have calculated in our previous steps. So substitute those values in this equation for checking. The torque T is equal to obtained 1100 Newton mm. Newton meter obtained, but in convert into Newton mm. So the 1100 into 10 to the power of 3 Newton mm. So substitute in this equation. So shear stress for the cast iron material need to calculate, but don't substitute the given value. The given permissible value is 15. How to check the given value is withstand or not? With calculated value. So calculated value always should be less than the given permissible stress. Then only your design is safe. Otherwise, again, we need to modify. Go back to first step and modify material or modify shaft diameter or key diameter, whatever may be. You have to modify till satisfy this condition. So now here substitute 125 D, capital D value, and inner diameter, shaft diameter is 55. So that the obtained shear stress, induced shear stress is 2.97 Newton mm square. The given value is 15. The given value is 15. So this value less than 15 megapascal. so that the above, you can say the above design is safe. So induced shear stress in the MUF is less than the permissible stress, therefore design of MUF is safe. So now obtain the safe condition so that you may fix the above values as a final values, whatever you calculated in previous steps. Now coming to the design for key. So key dimensions already you know. The dimensions are depends upon the diameter of the shaft. So the diameter of the shaft is here 55 mm obtained. So width of the key, so you may calculate by using standard diameters and width and thickness. Since the crushing stress for the key material is twice the shear strength, therefore a square key may be used. Here, which type of key is you have to assume. So not given particularly not given any type of key here. So that you may assume a rectangular key or a square key. For a rectangular key case, W is equal to D by 4 and T is equal to D by 6, T or H. And in square key, W width and T are same. T or H is equal to D by 4. Clear? So here given a condition is given the material crushing stress of the material is twice the shearing stress, so that the thickness of the key you may assume same. Now that the length of the key is the empirical relation length of the key is equal to L by 2. So length of the muff by 2. So this is 0.5 times of muff length. Or otherwise you may take here the standard empirical relation 1.5 times of D. The key dimension is 1.5 times of D. So where D is here shaft diameter. So any relation you may take. So that here length of the key also obtained. So next checking is crushing stresses induced, shear and crushing stresses induced in the key. So in our problem given shear stress, crushing stress for the key is given the crushing and shear stress 40 megapascal and 80 megapascal. So that need to check for the shear and crushing strength. So first you take consider shearing of the key. In case topic already we have studied. The torque transmitted T is equal to L into W into shear stress into D by 2. Similarly, for crushing L into T by 2 into sigma CS, the crushing stress multiply with D by 2. So 1100 Newton mm, 1100 into 10 cube Newton mm is equal to L into W into TS. L length of the key and W width of the key. So already we have determined in the previous step. Shear strength. The shear strength need to calculate. Don't substitute the given value. Have to compare with the given permissible value. So that now calculate shear strength. From this equation obtained, the shear strength is 22.8 Newton per mm square. So the given strength is shear stress is for the key material is shear stress is 40. So that this value less than 40 megapascal. So obtained value always should be less than the given permissible value. So now you can say your design is safe. so that key withstand the shear stress. Similarly, consider the crushing of the key, and again apply the torque transmitted by the key. T is equal to L into T by 2 into sigma Cs into T by 2. So here the shear is in key lengthwise and width. Length and width. The cross section here shown width and thickness. So crushing is like this, T by 2. So thickness of the key and length. So now when considering shear, we will take length and width, and considering crush length and thickness. So now substitute the above values and find the sigma Cs. So crushing stress in the key. So obtained crushing value is 45.6 Newton mm square. The given permissible value is 80 megapascal. So that the obtained value 45.6 Newton mm square is less than 80 megapascal. So now you can say your design is safe. So why? Because your calculated value is less than the 80. So up to 80 the key should withstand. So beyond the 80 megapascal the key will fail. So that you need to check for crushing and shear stress. If not satisfied this condition, now go to the previous step and modify some dimensions till satisfy this condition. So this is the design procedure for a coupling and keys. So here finally write down on comment. Here, induced shear and crushing stresses are less than the permissible stresses. Therefore, the above design is safe. Design of key is safe. For muff case, we have checking with crushing and started values. And then similarly for the key also we have checked for shear and crushing. So now the second problem is design a clamp coupling. So the another type of coupling, clamp coupling, to transmit 30 kilowatts at 100 rpm. The allowable shear stress for the shaft and key are 40 megapascal, and the number of bolts connecting the two halves are 6. So here extra, in addition to the shaft and key, the bolts are used 6. The permissible tensile stress for the bolt is given 70 megapascal. And also given the coefficient of friction between the muff and the shaft surface may be taken as 0.3, that is mu. So based on these given values, you need to design a clamp coupling. So for any design problem, first write down the given data, P 30 kilowatts and N 100 rpm and tau shear stress value for the shaft and key 40. Same for shaft and key, same value we given 40 Newton per mm square, and the number of bolts are here 6, and sigma T 70 megapascal, tensile stress, permissible stress, tensile stress, and mu also given. So now we will see steps. First step is design for shaft. So diameter already I told you. So dimensions of the key or dimensions, design dimensions, parameters of couplings depends upon the shaft diameter. So that's why first step is we need to calculate the diameter of the shaft by using torque transmitted by the shaft equation. So the shaft equation T is equal to 60P by 2 pi n. So again substitute here P value is 30 kilowatts converting to watts into 60 by 2 pi n. N is here 100 rpm. So obtained value is 2865 into 10 cube. So also know that the torque transmitted by the shaft T is equal to 5 by 16 into tau into dq. So consider here solid shaft. So substitute here calculated torque value and then shear value. Find out D. So find out D value. So here D is 71.4. So assume the standard value is 75 mm. So next step is design for muff. The diameter of the muff, the standard empirical relation is 2D plus 30. The diameter of the shaft is here taken 75. So calculated, the calculated value is 75 by using torque transmitted condition. The total length of the muff is L is equal to 3.5 times of D. Substitute D value and the obtained value is 262.5 mm. Similarly, design for key. So the dimensions of the key are here width and thickness of the key. For the shaft diameter 75 are, you may assume, you may take W is equal to 22 and width is equal to, thickness of the key is equal to 14 mm. So length of the key is equal to total length of the muff. So the obtained values are 262.5 and 22 and 14 respectively. Width, thickness and length of the muff. In this, the new one is bolts. Why? Because the given coupling is clamp coupling. The two shafts are connected with the help of muff, key and bolts. Here number of used bolts are 6. So bolt dimensions need to design. So let assume dB is root or core diameter of the bolt. And again apply the torsion equation, torque transmitted T is equal to 5 by 16. Here applied here 5 by 16 into tau into dq. This is for solid shaft. But in this case, the bolts case, the torque transmitted is equal to pi square 16 and then T is equal to pi square by 16 into mu coefficient of friction into diameter, the root diameter of the bolt square into tensile stress. Tensile stress into number of bolts and diameter of the shaft shown in this. So now in this substitute the calculated values. T already you know 2865 into 10 cube, pi square 16 the mu value, coefficient of friction, and root or core diameter of the bolt is dB. Substitute sigma t. Door diameter or diameter of the bolt need to calculate, not available. Sigma t calculate, substitute, and n value 6 and d also substitute. Suppose sometimes they may not given this bolts number of bolts. In that case, you may assume 4, 6 or 8. So here the obtained value T is equal to 5830 dB square. Now calculate dB. So diameter root or core diameter of the bolt. So that is 22.2 mm, the diameter, core diameter of the bolt. The standard core diameter of the bolt for core series is 23.32 mm. So this value you have to take from the design data book. In design data book, the tabular in bolts topic, tabular form is there. For different various series, the standard core diameters are available. And the nominal diameter of the bolt is 27. So that the bolt, the design bolt is, the designation is M27. So metric type of bolt, and series is core series. The standard nominal diameter is 427. So next problem, the third problem on cast iron protective type flange coupling. So in the previous case, we have learned rigid type of coupling, muff coupling, and or sleeve coupling, and clamp coupling. This one also protective type or unprotective type of flange couplings are classified under rigid type only. But the only difference is here, the flanges are used here. These flanges are integrated with the shaft. So having the outer diameter and a pitch circle diameter for placing the bolts. This cast iron protective type flange coupling to transmit 15 kilowatts at 900 rpm from an electric motor to a compressor. The service factor may be assumed as 1.35. So sometimes this value is not available, may not given in the problem. So in that time you may assume the service factor if need. So 1.35. And the following permissible stresses also given. The shear stress for the shaft, bolt and material, key material 40. Crushing stress for bolt and key material 80 megapascal. And shear stress for cast iron is 8 megapascal. So also he has asked draw a neat sketch of the coupling. So after completion of your design, you need to draw the complete sketch of a coupling with calculated values. So these values need to check for key material for shear stress and shaft material for shear stress. Similarly, the crushing stress for the bolt and key and cast iron need to verify. So first one is given data P and N value. The service factor, here newly added this term service factor 1.35, and shear stress for key, shaft and bolt material are 40 Newton for mm square. And similarly crushing stress and shear for the cast iron material. So the shear stress for the cast iron 8 megapascal given, convert into Newton for mm square. The first one is design for hub. The hub dimension need to calculate. This is the diameter. So the T max is equal to, the maximum torque is equal to here 1.35 multiply with 159.19. So what is this 159.19 is the torque. So mean torque. So mean torque obtained from this relation 60p by 2 pi n. So in this value, in this torque, T mean torque, P substitute and 60 and N, so you will get 159.13. But the service factor is given, so you should multiply with the service factor with T mean factor. So obtained T max is equal to service factor Ks multiply with T mean. So service factor is 1.35 and mean torque is 159.13. So obtained value is 215 into 10 cube Newton mm. So this is our maximum torque. So we know that torque transmitted by the shaft is T max is equal to pi by 16 into shear stress into dq. Here to substitute the maximum torque. T max. T mean available from the power transmitted equation. So T max obtained from torsion equation. So pi by 16 into shear stress into dq. Here unknown value is d. So unknown value is d. So here find out d value. So the obtained d is 35 mm. So that we know that the outer diameter of the hub is d is equal to 2 times of the diameter of the shaft. The shaft diameter obtained is 35. So here flanges means, so like this. So this is one plane. Another plane is sorry. So this is plane coupling. This connected with the alpha for 2 bolts. So in this, this one is the diameter of the shaft and outer diameter of the hub, that is capital D. This capital D is equal to 2 times of the D as per the standard empirical relation. Now substitute the diameter of the shaft, then the diameter of the hub or shaft diameter. So now 70 mm obtained. The length of the hub is 1.5 times of the D. So length of the hub and obtained value is 52.5 mm. So now let us check for the induced shear stress for the hub material, which is cast iron. Considering hub has a hollow shaft. So hub having inner diameter and then outer diameter. So that consider as a hollow shaft and take the maximum torque transmitted equation. So T is equal to pi by 16 shear stress into dq for solid shaft having only one diameter. For hollow shaft, pi by 16 tau into capital D to the power of 4, small d to the power of 4 by capital D for hollow shaft. Here, the hub is considered as a hollow shaft. So apply this torque transmitted equation. The torque transmitted equation. So now substitute calculated values. T max 215 10 cube obtained in the previous step. 215 into 10 cube. And then substitute the outer diameter and inner diameters. The obtained value is 63.147. So that calculate the shear stress is 3.4 megapascal. So the given permissible value for the cast iron material is 8 megapascal. So that this value is, the obtained value 3.4. So the 3.4 less than the 8 megapascal for the hub material. So that we can say the above design is safe. So next second step is design for key. The key dimensions so depends upon the diameter of the shaft. Here crushing stress for the key material is twice its shear stress. So that in this case you may assume the type of key is square key. Suppose not equal, the crushing stress is not twice of its shear stress. So in that case you may assume another key like rectangular key. So here in design data book shown this table, find the shaft and shaft of 35 mm diameter. So from this value take from design data book. K. Mahadevan book is available. So that here shaft diameter is 35 mm and width is 12 and thickness of the key. So the length of the key is taken equal to the length of the hub. So here capital L is equal to small l. Now check the induced stresses in the key by considering it shear and crushing. For the hub material already we have verified the induced shear stress. So because here hub material is cast iron and your key material is different. Now, so that induced shear stress by the key, considering it shearing and crushing, and considering the key in shearing, so find the torque transmitted, maximum torque transmitted. So the maximum torque transmitted, while considering shear, T is equal to area multiplied with shear stress into D by 2. So L into W into shear stress of the key into D by 2. So the length is 52.5. Calculated. The width also you have taken from the standard values from design data book, and the shear stress need to calculate. And the D diameter of the hub or shaft already calculated. Now find out shear stress. The shear stress for the key is 19.5 megapascal. Considering the key in crushing, we know that the maximum torque transmitted is apply this equation and again calculate crushing stress. Now compare these two values with the permissible values. So the permissible values are less than, so these calculated values are less than the permissible values. Obtained while considering shear is 19.5 and 39 megapascal under crushing. So the given values are Here, crushing for the bolt and key material 80 and 40. So that 40 and 80 take here less than 40 megapascal and less than 80 megapascal. Obtained values are less than the given values. Then you can say the above design is safe. Next, third step is design for flange. The thickness of the flange is taken as 0.5 times of D. This is the standard empirical relation. Now, check for the induced shearing strength in the flange and crushing also. So, the maximum torque transmitted apply condition, that's T max, and then again calculate shearing stress value. Here, flanges, junction of the here, the considering the flange at the junction of the hub in shear. So already as we have calculated in clamp coupling. So take that relation. Here substitute the flange thickness as 0.5 times of D shaft diameter and calculate shear stress. So the obtained value is 1.6 megapascal. So this is less than the 8 megapascal. The given permissible value is 8 megapascal. Therefore, the above design of flange is safe. So last step is fourth one is design for bolts. So what is the diameter of the bolt? So here diameter of the shaft is 35 mm. Let us say you may assume the bolt number of bolts and the pitch circle diameter of the bolts are n is equal to 3 and the pitch circle diameter is 3D. Diameter is 3D and the number of bolts are 3. So flange having here pitch circle 2, 3, 4, 5. So like this the bolts are arranged. So the pitch circle diameter will draw again here. So this is the shaft and this is the pitch circle diameter. On this pitch circle here bolts are arranged. So this diameter is pitch circle diameter. This is hub diameter, hub outer diameter. This is a hub inner diameter. So nothing but shaft diameter. This is bolt size. Here small d1. Bolt nominal diameter. So we know that the torque transmitted is due to the shear stress. T is equal to 5/4 into d1 into shear stress into number of bolts multiply with half of the pitch circle diameter. So take this equation. In this all values are known values and the only thing is the diameter of the bolt d1 is unknown, small d1. So now calculate the small d1. The small d1 the obtained 43.43 or d1 square is equal to 43.43. So d1 is equal to 6.6 mm. This is our final nominal diameter of the bolt. So like this, you have to calculate the diameter of the bolt. So after that, by using design data book tabular form, so assume the course thread, the nearest standard size is, you can say, M8. For this nominal diameter 6.6, the standard diameter, the standard size of the bolt is M8 bolt. So other remaining proportions, or if any are there for the planes, you can take outer diameter of the planes is diameter is equal to 4 times of the d. Use empirical relations only. And the thickness of the protective circumferential planes. So this one is a protective planes. So that protective plane is 0.25 times of d. So substitute the diameter of the shaft, and the obtained value is 10 mm. So after that, he has asked to draw a neat sketch for a protective type planes coupling. In this shown, the protective type coupling, shaft 1 and shaft 2, and this one planes and another planes, bolts, M8 bolt here, and here protective cover taken TP, and the TF is the here plane thickness, plane thickness. So each and everything, all values we have calculated, and the key dimensions also have designed. The hub dimensions also we have calculated. So finally, you need to draw sketch for a protective type lens coupling by using the above calculated design values, design parameters. So I have taken references like this: V. Bandari, a textbook for design of machine elements, and R.S. Kurmi, and R.L. North. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.